All right, welcome back. So now we're going to deal with, well, how to deal with real load conditions when you usually have more than one load. For example, in this picture I have here, it's a combination of two examples we had before, where the red constant load could represent the mass of the beam, or the weight of the beam, and the green load is like a snow load. So a way to approximate these real life conditions is to use multiple loads. So you find each equivalent load, find each equivalent load and its location. Okay, so essentially for this one you would have two resultant loads or 2-point loads acting at two different places, one right in the center and one to the 3/4 of the way over from the left. So for a we saw that for planar solids, okay, with constant density and constant thickness, okay, the location in the x direction of that force is the integral from 0 to L x times the weight distribution function dx over just the force, which is the same as the numerator with just the weight distribution function, the integral of that. Okay, W of x equals the load curve. Okay, now you can also do this in the y direction. All right, and you get a similar thing. You get a y bar, the integral of the moment arm from where you're measuring the moment in the y direction times the load function in the y direction dy over the load in the y direction. Right now, this is useful because what we can do is we can take multiple or complex distributed loads and we can approximate, or we can break into multiple regular shapes. So you can take multiple or complex loads and break into regular shapes. Then you solve and add your results. All right, so for example, here's what I mean by that. You have right here a complex load. Say it's made of the weight of the beam plus some other load that's on it, whatever it is. Okay, so I actually drew this incorrectly. This is supposed to go to here, and this should go like this. So, all right, little touch up there. Okay. So what we can do is break this up into multiple shapes. Now, there's nothing sacred about the way I did it here. I broke it up into 3 rectangles and 2 triangles. We know how to deal with those. Those are easy to deal with. Nothing says that you couldn't draw a rectangle, a single rectangle, the whole length of the beam, and then have another, going across here, and then making that R2 smaller. I guess what I mean is here. You could have made a rectangle like this, and then another one like this, right? And then the same 2 triangles, right? That would actually be an easier way to solve it. Probably should have done that, but I didn't do that. So anyway, it doesn't matter. You're going to get the same answer no matter what you come up with, as long as it's as long as you added your areas properly, you're all set. So remember, because we're dealing with planar solids that have constant thickness and constant density, then the centroid and center of mass are in the same location. So we can use geometry. So basically what's going to happen is this. We know that the center of mass for a rectangle is in the middle of that rectangle. So we can just put those locations right in the middle of the rectangle. We know where it's going to be for a triangle. You can look that up in your table. So that's basically how we're going to handle those types of problems. Now, for planar solids, with constant density and thickness, in the way I've been drawing these, that would be the z direction. We can simplify our expressions. All right, so basically, if you were to go through this, what happens is gravity and density drop out of the numerator and denominator. When you assume constant density. All right, so what this boils down to, and this is the equation form of what I just showed you visually, right? Is the location of that equivalent force. X, this is the form we've been using. Let me make that a little neater. This is approximately equal to, or can be simplified, assuming the above, we can do a summation. Replace the integral with a summation from I equals 1 to n xi ai over. Okay, so n is the number of shapes that you've broken your load into. So all you need to do is just look at the shape of the load distribution. The material properties don't really come into play, right? Because we have constant density. So note that the analogous y location is the same thing. You're going to get a summation from I equals 1 to n of, not equals, of yi, the moments of each area over each area. Okay, so these guys are going to be more helpful when you get more complicated beam shapes, like, we've been dealing with this sort of thing, right? But what if you get something that has this sort of shape? Okay, so it's a more complicated cross section, so we deal with it in parts. Okay, and that is where I'm going to stop for now. That's enough to take in. Take a shot at those homework problems, and the first couple. And on Wednesday, I'm going to start right in with a problem where we use this to divide a load up and find the resultant by using that summation method. And then we're going to go from there into moments of inertia, which is going to take us into our next topic. So that's on the horizon for Wednesday. Till then, have a happy Sunday, and we'll see you later.